In this section, we're going to look at another operation for vectors. We call it the vector product or the cross product. Now let's do a quick recap on what is the definition of scalar product. Alright, so for the scalar product, from the name itself, the result of the scalar product between two vectors will be a scalar. Alright, and we also name it as a dot product because we actually use the symbol the dot to signify the operation between the two vectors. So if we were to take a look at the vector product, also called the cross product, we would deduce that the vector product, the result of the vector product between two vectors would be a vector itself, and perhaps the symbol that we use, alright, to signify the operation involving the vector product is a cross. Okay, so let's look at the definition. The vector product of two vectors, for example a and b, is given as the magnitude of the vector a times the magnitude of the vector b times sine of the angle in between the two vectors, in this case is theta, times the unit vector n. The unit vector n is a vector perpendicular to both a and b. Alright, so if we were to study this definition in greater detail, we realize that these three terms, the modulus of a and b and the sine theta, is a scalar, whereas the vector, the unit vector here, is a vector. So if we were to look at this multiplication to the vector, the right hand side actually will remain a vector, and therefore we can safely say that when we take two vectors and do a vector product between them, the result is still a vector. Now the direction of A cross B follows the right hand rule. So if you were to look at this setup, alright, the thumb actually points upward when you take the vector A with your fingers curling towards the vector B. When this happens, your thumb will be pointing up, and that will be the direction of the vector A cross B, and this vector A cross B is actually perpendicular to both the vector A and the vector B. So this is the vector product or the cross product.
Right hand thumb rule. The thumb rule states that if the fingers of the right hand are curled in such a way that they point along the direction of rotation from vector A to vector B through a small angle, then the thumb points in the direction of the cross product of vectors A and B. Note that the cross product of two vectors will not obey commutative law.
So if you use the right hand thumb rule to do a vector product of starting with B first, cross A, that means you're going to curl your finger from B to A, you realize that your thumb will be forced to move downwards, as what you see in the diagram in the red arrow here. So B cross A is actually in the opposite direction. One thing you should notice is that A cross B and B cross A will be equal in magnitude, but they are actually in the opposite direction, and thus we can conclude that A cross B is actually equals to the negative of B cross A. So from the definition of the cross product, we would realize that A cross B will be a vector perpendicular to the plane containing the vector A and the vector B. So in this setup, you can see the plane here containing the vector A and the vector B. The angle between the two vectors is theta. So when we do a cross product between the vector A and the vector B using right hand thumb rule, we would see that when we cross A and B, we will actually get the vector A cross B pointing upwards, and this vector is perpendicular to both A and B. Now n is a unit vector. Being a unit vector, it has a magnitude of 1 unit, and this vector is perpendicular to both A and B and in the same direction as A cross B. The direction of n, as what we have mentioned, will be determined by the right hand grip rule. So when we look at this setup, when we do a cross of B cross A, the right hand grip rule will force us to actually have the vector B cross A pointing downwards, such that now let's take a look at the basic properties of the cross product. When we take A cross with itself, we will actually get the zero vector. This is because the angle between A and A is 0. The reason for this is, if we use the definition of the cross product, A cross A will be equals to the magnitude of A times the magnitude of A times sine of the angle in between the two vectors. Because angle between the two vectors is 0, sine 0 will actually give us 0 scalar. So the whole thing will actually become 0 times the unit vector n, such that we will actually get the 0 vector. A cross B is a vector perpendicular to A and B. It means that this vector will be perpendicular to the plane containing both A and B. So if we were to look at this plane here, the vector A and the vector B is on this plane. When we do a cross between the two vectors, the vector A cross B will be perpendicular to both these two vectors and also to the plane containing these two vectors. In fact, this perpendicular vector has a special name. This perpendicular vector is called the normal vector of the plane. A cross B is equals to the negative of B cross A. We have seen this before, and thus we should note that the cross product is not commutative, unlike the dot product. In the dot product, we can actually write this: A dot B is equals to B dot A. In the cross product, we cannot, because it is not commutative, as we can see that even though the magnitude is the same, the direction is actually opposite of each other. The last two properties of the cross product is that the distributive law still applies for the cross product, and the scalar multiple properties for vectors still apply for cross product. Now what can you say about vectors A and B when A cross B is equals to 0? This would only mean that either A or B are both 0 vectors, or one of them is a 0 vector. Next, we're going to look at the cross product of two vectors in the 3D Cartesian space. Now recall that I and j are unit vectors pointing in the positive x and y direction respectively. I and j are also the base vectors. Now the vector I cross j, using the definition of the cross product, will be equals to magnitude of I times magnitude of j times sine of the angle between the two vectors and times the unit vector perpendicular to both I and j. We know that the magnitude of I is 1 as well as j is also 1, so we have 1, 1. Now I and j are perpendicular to each other, so the angle in between them is 90 degrees. Alright, so when we evaluate this, we actually get the unit vector itself and perpendicular to both I and j. Now using the right hand rule, this unit vector is actually pointing in the positive z direction. As we have denoted before, this positive z direction has a unit vector of 1 also, and we call this the vector k. Remember that this is a base vector as well, parallel to the z-axis. Now if we consider j cross I instead, the thumb points downwards in the direction of the negative z-axis, pointing this way. The unit vector n in the cross product formula is therefore negative k, and we can actually explain it with the use of the definition of the cross product as well. Now when we take I cross j, we will actually get the base vector k. When we take j cross k, we get the base vector I, and when we take the vector k cross I will get the base vector j. For these base vectors I, j and k, to remember these results, think of arrows pointing from I to j to k and back to I as shown here. So I to j to k and then back to I. The cross product is positive if it is flowing in the direction of the anti-clockwise motion. So anti-clockwise motion, I cross j equals to positive k, k cross I equals to positive j, j cross k equals to positive I. Now certain things that you need to take note is that I cross I will give you the 0 vector. The reason is we can still use the definition of the cross product. I cross I will give you magnitude of I times magnitude of I times sine of the angle in between them, which is 0, which will give us 0, and therefore 0 times the unit vector perpendicular to both I and I, alright, will give us the 0 vector. We are now ready to derive the formula for cross product of two vectors in the 3D Cartesian form. For example, if we are given these two column vectors, in order for us to evaluate the column vector, we actually change each of these vector into the ijk form, and then we cross product each of these terms. So for example, a1i cross with b1i plus a1i cross with b2j plus a1i cross with b3k, and so on and so forth. Now let's try to simplify this long set of results. A1 b1 I cross I. We saw before that I cross I will give us the 0 vector. A1 b2 I cross j. I cross j will give us the positive k. A1 b3 I cross k. I cross k will give us the negative j, and so on and so forth. With this result, we can reduce it to this, and then we realize that we can actually rewrite this into the column vector form by grouping the x component, y component, and the z component. So if we group the x component, we will have a2b3 minus a3b2. For the y component, we would have negative of a1b3 minus a3b1. Last but not least, for the z component, we would have a1b2 minus a2b1. There is a specific way of memorizing this formula. Let's take a look. Now, so if we are interested to find the x component, what we will do is, in the original two column vectors, we will cover the x component like what you see here, and then based on the arrow, we will cross multiply the numbers starting with the blue arrow. So you would have a2 times b3 minus a3 times b2. So you will get this. So for the z component, it is still the same way. We will cover the z component in the original column vectors like this. Still apply the multiplying of the numbers starting with the blue arrow. So we have a1 b2 minus a2 b1. So we'll get the z component. Similarly, for the y component, we will cover the y components in the original column vectors. Then we still multiply using the blue arrow first, a1 times b3 minus a3 b1. The different thing about the y component is that we must put a negative sign after we have done that multiplication process. So this is a way for us to evaluate the cross product between two column vectors. Please do not use this method to find the cross product between two column vectors. It is not the method. The method is to use this algorithm. Alternatively, we can find the result of the cross product between two column vectors using the determinant method. Now, if we want to find the result of the cross product between these two vectors, we can form this determinant. I, j, k. Put the first column vector in this way, a1, a2, a3, and the next column vector in this way, b1, b2, b3. Using the determinant method, in order for us to find the I component, we cover the I row over here. Then we will write, then we will have this. In order for us to find the j component, we will cover the j row here. Then we will have this. In order for us to get the k component, we will cover the k column here. Then we will have this. So in order for us to get the x component, y component, and z component, what we need to do is to evaluate this, and this. So for us to get the x component, what we will do is we will multiply these numbers in this way. So if you notice, we will get a2b3 minus b2a3. And for the y component, we will get minus a1b3 minus b1a3. And the last z component, we will get a1b2 minus b1a2. And now let's look at some examples in evaluating the cross product of two column vectors using the first method. Alright, so in part A we have I plus 2j minus k cross with 2I minus j plus k. Now these two vectors can be easily written into two column vectors. Alright, so to evaluate, to get the result, in order for us to get the x component, we cover the x row in the original vectors, and then we cross multiply the numbers in this way. 2 times 1 minus negative 1 times negative 1. Then you get the result in the x component as 1. To get the y component, we cover the y row, and then we cross multiply the numbers in this way. 1 times 1 minus negative 1 times 2. And then we shouldn't forget the negative for the y component. We will get negative 3. Lastly, to get the z component, we cover the z row in this way, and then we get the multiplication of the numbers in the same way. 1 times negative 1 minus 2 times 2. Then we'll get the final result. I will leave you to figure out the solution for part B. Now, whenever we get the result of the cross product between two column vectors, it is good for us to actually check the correctness of the cross product. Alright, so recall that A cross B is a vector perpendicular to both A and B. So for A, we will have worked out the cross product correctly if this result here is perpendicular to both the two vectors that we have used. Alright, so if you notice from this setup, A cross B is actually perpendicular to both the vectors A and B. So how do we confirm whether this column vector result is correct? We can actually do the dot product between this vector and each one of these vectors. If the result of the dot product between this vector and each one of these two vectors is 0, that means indeed this is the correct cross product between the two vectors. So for example, if I want to check whether this result is the correct cross product, what I will do is I will take this vector and do a dot product with 1 to -1. It is 0. Similarly, for the other vector, it is 0, and hence this vector is indeed perpendicular to both these two vectors, and therefore this result of A cross B is correct. Now, what are the uses of the cross product? The first important application of the cross product is to find the vector perpendicular to two other vectors. So if I have two vectors on the same plane like this, A and B, and if we want to find the vector perpendicular to both A and B, alright, what we can do is we do the cross product or vector product between the two vectors. So in this example, you are asked to find the vector perpendicular to both vector A defined as I plus 2j plus 7k, and the vector B defined as 3i minus j plus 6k. Alright, so for us to get the vector perpendicular to both A and B, we do the cross between them. Make sure we rewrite the I, j, k form of the two vectors into the column vectors. Alright, so using the algorithm that we have just seen, we can get the column vector. And in order for us to check whether this column vector that we have obtained from the cross product of these two vectors is correct, we take this and dot with each one of these and see whether it is equals to 0 or not. Now the question actually asks us to find a vector perpendicular to both these two vectors. Alright, so any vectors which is parallel to this vector will be a valid answer to this question. Okay, in this example, we are given 3 points A, B and C with the position vectors in the IJK form, and we are supposed to find a unit vector perpendicular to the triangle ABC. Now if we were to look at this setup, we can see the triangle ABC. It is actually lying on a certain plane. The unit vector perpendicular to the triangle ABC, if we were to look at this setup, we define it as the n hat. This is the unit vector we are talking about. Okay, there is a special name for this unit vector, as I've mentioned before. This is actually the normal of the plane. Vector which is normal to the plane is actually perpendicular to the plane itself. Alright, so how do we start to find this unit vector perpendicular to the triangle ABC which is lying on this plane? So we need to get any two vectors formed by any of the 2 points in this triangle. So we can take AB the vector and also AC the vector. Alright, so what we can do is we find what is the vector AB first. Alright, so OB minus OA. Right, and then AC is OC minus OA. Right, so AB is OB minus OA, AC is OC minus OA. We will get AB and AC. Alright, AC, if we were to look at the result, is actually -2, 2 and 4, and this can be reduced as 2, -1, 1, 2. Alright, so for most of cross product, if we want to find the cross between two vectors, we try to simplify the column vector by factorizing out whatever numbers that we can. Alright, so that when we do the cross product, we will be doing it a little bit simpler because the factor 2 is taken out. Okay, so in this case, when we do the cross product, we are actually doing the cross product between this vector and this vector, because the two being a scalar multiple, we can actually take it out of the process of the cross product. Okay, alright, so based on the result of the cross product, we actually have negative 2, 7, 1, 3, or 2 of negative 7, negative 1, negative 3. Alright, so a vector perpendicular to this plane is basically 7, 1, 3. Now you could also use minus 14, minus 2, and negative 6. You could also use this vector, but because this is not factorized in the simplest form, alright, we try to avoid using this. Okay, so what we can do is we just take the vector 7, 1, 3, or you could also even take the vector negative 7, negative 1, negative 3. Alright, so in this example, we take 7, 1, 3 as a vector perpendicular to the plane. So the unit vector, alright, represented by n hat, is just the vector divided by the magnitude. Now, the second application of the cross product is to find the area of triangle and also the area of a parallelogram. Now, consider a triangle ABC with the angle BAC as theta. We know the area of the triangle ABC using formula is a half AB and AC sine theta, where AC sine theta is actually the height of this triangle. Now, the line segment AB, the length of the line segment AB and the length of the line segment AC is actually the magnitude of the vector AB itself and the magnitude of the vector AC itself. Alright, from the definition of the cross product of the two vectors AB and AC, we will actually get modulus of AB times the modulus of AC times the angle in between the two vectors, which is theta, and times the unit vector perpendicular to both these two vectors. Because of the modulus, we will apply the modulus to each one of these terms, and we realize that the modulus of the unit vector n hat will actually be 1. Alright, so our expression here will be reduced to this, and this happen to be the double of the area of the triangle. So the area of the triangle ABC can be given as half of AB cross AC modulus, as twice of the area of triangle is equals to the whole parallelogram. So therefore the area of the parallelogram is basically AB cross AC. So you will notice that if you want to find the area of the parallelogram, what you need to do is just find any two vectors that form the sides of the parallelogram and then cross it and then find the magnitude. So in general, area of a triangle given a triangle ABC is basically half modulus AB cross AC, or half modulus BA cross BC, or half modulus CA cross CB. So basically, if you want to find the area of a triangle, what you need to do is use the formula half modulus of, take any two vectors and then cross them. And the area of parallelogram is basically double the area of the triangle, so you will eliminate the half. Alright, so again you just choose any two sides of the, so you just choose any two vectors that represent the two sides of the parallelogram. Example 24 is an easy example of finding the area of triangle. Now in this example, you're given 3 points with coordinates 2, 0, negative 3, 1, 4, 5, and 7, 2, 9. So in terms of the diagram, it is actually a triangle. Okay, so each one of these coordinates can be written as the position vector of each one of those points, and they are given by these column vectors. So OA, the vector, is equals to 2, 0, negative 3. OB, the vector, is equals to 1, 4, 5. OC, the vector, equals to 7, 2, 9. So take note, the coordinates of the point A is given in this form, while the position vector of the point A with reference to the origin is given in this form. Why is this important? Because sometimes the question actually asks us to find the coordinates of point A, so we need to give it in this form. However, sometimes the question do ask us to find the position vector of the point A, and therefore we have to give it in this form. So how do you find the area of this particular triangle? So what we need to do is basically we need to choose any two sides that forms a triangle. So let's say we choose AB, the vector, and AC, the vector. Alright, so what we need to do is just cross those two vectors, then we get a new vector here, and applying the area of the triangle, which is basically half of the magnitude of this, we will get the area of the triangle. The third application of the vector or cross product is to find the shortest distance from a point to a line. So let's look at this setup. I have the point A and the point B forming a line segment. I have a point C over here. So the shortest distance from the point C to the line AB is by connecting the point C to a point D, where the point D is called the foot of the perpendicular of point C to the line AB, such that CD is perpendicular. So CD will actually form a line which is the shortest to the AB, and this line must be perpendicular to AB. Alright, so D, as what I've already said, is called the foot of the perpendicular from C to the line AD. Now, how do we use the vector product to find this distance? Now, let's do a quick recap. Previously, when we used the dot product, right, is used to find the distance AD over here. So the formula for the dot product is we take the vector AC, we dot with the unit vector parallel to the vector AB. Alright, so in this case the unit vector is actually P hat. This vector is P, so the unit vector is P hat. So the formula is this. Alright, so when we use this formula, we will actually get this distance. Now similarly, we can also use a similar kind of formula to find this distance. Now let's take a look. In the triangle ACD, right, sine theta is equals to opposite side divided by the hypotenuse, as what you can see here. Now CD is equals to, therefore, modulus of AC times the sine theta. Now let's take a look at the definition of the cross product. So in this case, right, so in this case, if I were to take the vector AC, I cross with the unit vector P hat, by definition, alright, we will have modulus of AC times the modulus of the unit vector P hat times sine of the angle in between them. Since P is parallel to AB, the angle between AC and P, or the unit vector of P hat, will be theta as well, so sine theta, right? And then N hat is the unit vector perpendicular to both the vector AC and then the vector P, right? Remembering that we have the modulus outside here, so we will retain the modulus, and in this case this is a unit vector, so we get 1. Then we have the sine theta, and then down here the unit vector modulus of the N hat will also be 1. Alright, so from this expression we will be left with exactly this. Alright, so based on this expression, we can see that we will actually get AC modulus times sine theta, and the modulus of sine theta is exactly sine theta, because theta can be either be acute or obtuse, and sine theta will be positive whether theta is acute or obtuse. That means in the first and the second quadrant of the theta. Alright, so if we were to take a look at this expression, is exactly what we have here. Alright, so therefore the length CD is basically AC, the vector, crossed with the unit vector P hat, which is parallel to the vector AB. In summary, the shortest distance from the point C to the line AB, alright, is given by the modulus of the vector AC cross it with the unit vector parallel to AB. In this case, the unit vector parallel to AB is actually the unit vector of the vector P over here, so P hat. Alright, or another version of the same formula is we rewrite the vector in this form, and this basically is the unit vector parallel to the vector AB, where the unit vector is equals to the vector AB divided by the magnitude. So in summary, if we have the vector AC, the vector AB, and if we are interested to find the distance Cn, basically Cn is equals to the modulus of the vector A cross with the unit vector parallel to the vector AB, in this case B hat. And based on what we have done before in terms of the length of projection of the vector A onto the vector B, alright, the distance from A to N can be calculated using the formula modulus of A dot with the unit vector parallel to AB, in this case is B hat. Now in the previous section, we also had a formula where we wanted to find the projection of the vector A onto the vector AB, which is the vector AN itself, and the formula was given as we take the vector A, we dot with the unit vector parallel to the vector B, which is in this case B hat, we get a scalar, and then we multiply this scalar to the unit vector itself. Right, so is it possible for us to deduce the same formula for Cn? That is, we say Cn therefore is equals to A cross B unit vector and then multiply by the unit vector itself. Can we actually use the same formula in this case just by changing the dot to the cross, because the distance between C and N is basically just by changing the dot to cross? Can we do this? Now this is not allowed because this is not the correct formula. Alright, so in order for us to actually find the vector Cn itself, basically we need to go and find An, perhaps using this formula, and then find Cn by using the triangle law. Now Cn can also be found in a different way. The magnitude of the vector Cn, or the line segment Cn, the length of the line segment Cn, instead of using this cross product formula, we can actually just use the Pythagoras theorem, because we can always find An using this formula. We already know the length of this hypotenuse, which is the magnitude of the vector A. Alright, so using Pythagoras theorem, we will be able to find Cn as well. Now what is the advantage of this using this formula? The advantage of using this formula is at times vectors question don't really need us to find this length of projection An. Alright, but sometimes the question do ask us to find the length of projection An, so it will be meaningful to just use the Pythagoras theorem to find Cn. Now let's take a look at a quick example on how to apply the vector cross product. Alright, so in this particular question, the triangle LMN, such that Ln and Mn are perpendicular, and Ln happens to be parallel to a vector 2i minus 2j plus k. So we purposefully put this vector as the vector P. Alright, so the vector P in terms of ijk is 2i minus 2j plus k, and this can be written in the column vector form. Alright, the line Ln is actually the length of projection of the vector Lm onto the vector Ln. So using the dot product formula, alright, we will be able to get that particular length. Right, so the application is by applying this formula directly. Okay, so next we want to find the length of the distance from M to N, and we already know the formula is by using the cross product. Alright, so we're going to take the vector Lm, we're going to cross it with the unit vector parallel to ln. In this case is the unit vector of p hat. Alright, so p hat is actually the p vector divided by the magnitude. Alright, so using this formula, alright, we will be able to get mn itself. In the next example, we are given three position vectors for point A, point B and point C as these column vectors. We're supposed to find the length of projection of AC onto AB. Supposed to find the perpendicular distance from C to the line AB. Supposed to find the vector NA, where N happens to be the closest point on the line AB to C. Now, doing this question without drawing the diagram is going to be difficult. Before we go ahead to find the length of projection of AC onto AB, we go ahead to find what is the vector AB first. Okay, and then go ahead to find the vector AC. Alright, now let's take a look at the diagram. Okay, so the diagram that we can draw is some sort like that. Alright, so we have the vector AB over here and the vector AC over here. And we already found what is the vector AB in column vector form and AC in the column vector form. The point N is in fact the foot of the perpendicular from the point C to the line AB. Okay, so in part A, we're supposed to find the length of projection of AC onto the vector AB, which is actually this green part here. Alright, so we should use the dot product formula that we've seen before to find the length of projection. Now, in this example A, I started off by drawing the diagram such that this angle, if you notice, is actually an acute angle. However, if we were to look at the working, this part here, AC dot AB, is actually negative. So what does it imply? It actually implies the angle between AC and AB, alright, is not acute. The angle between AC and AB is not acute, but in fact, it is actually obtuse. So the angle is actually obtuse. Alright. So the correct representation of the diagram is such that this angle is obtuse. But if you had started drawing the angle such that this is good, is not actually very significant. Alright. So now the next part is to find the perpendicular distance from C to the line AB. So C to the line AB. Now as we have already found what is this distance, and we can also find what is this magnitude of the vector AC. Alright, so for us to find Cn, alright, we can use the cross product method that we have just learned, or we can use the Pythagoras law. Okay, so if we wish to apply the cross product method, okay, basically just apply using the formula. Alright, then we will be able to get the actual distance of C to N. Now, in the last part of the question, we are asked to find the vector NA. Alright, so the vector NA, by definition, is actually we get the magnitude of NA and then we scalar multiply it to the direction, and this direction happens to be the unit vector in the direction of NA. And we know that NA is in the same direction of AB. Alright, because the correct diagram is here, right? And this, we know that this angle is obtuse and NA is actually pointing in the same direction of AB. So what we need to basically do, we already found the magnitude of NA was 41/7. So we just multiply with the unit vector parallel to NA and in the same direction to the AB. Alright, then we will get the vector NA itself. Now alternatively, we can always find AN. Alright, so we can always find AN by using the formula that I've shown you before to find the projection vector. Alright, but if you found AN, you realize that AN is actually negative of NA. Alright, so to find the final result NA, you just negative of this vector, you will be able to get NA itself. Now in the last example, we are given 2 points A and B with position vectors A and position vector B respectively. And then the point M divides AB in the ratio 2:3. Alright, so in terms of the diagram, we can draw it in this way. So M divides AB in the ratio of 2:3. OA is the vector A, OB is the vector B. Right. Now in this question we are asked to write down the vector OM in terms of A and B. And then for part 2 and part 3 we are given the modulus of A has a value of 2, modulus of B has a value of 3, and the angle AOB is 60 degrees. Alright, we're supposed to show the length of OM is this length. And then the last part we're supposed to find the shortest distance from the point A to OM. Alright, expressing the answer in the form of K times the modulus of A cross B, where the exact value of the K is to be determined. Alright, now in this question, part 1 they say write down OM, right? The vector OM. So indeed we can actually write down, because we can write down the vector OM immediately using the ratio theorem. Alright, so this is not too difficult by applying the ratio theorem. The objective of part 2 is to find OM. Alright, now we have already obtained OM as 3/5 A plus 2/5 B. Now the approach that we're going to take is, remember when we take two vectors, we do a dot of the two vectors with itself, we will actually get the magnitude of the vector squared. Alright, so we can actually get the magnitude of the vector by square rooting this value. Alright, so that is the approach that we're going to take. Alright, and in this case we are able to square root this value, because we know that this value is going to be a positive scalar, because the angle between them is 0, so cosine 0 is 1, so it will be a positive value here. Alright, so this is actually possible. Alright, now so we take this approach, we apply it to OM. So magnitude of OM squared is equals to the vector OM dot with itself. So now we will do the dot product by doing the dot product term by term. Okay, so from this line we will realize that A dot A is the modulus of A squared, B dot B is the modulus of B squared, then A dot B, applying the definition of the dot product, will give you the modulus of A times the modulus of B times the cosine of the angle in between. Alright, and in this question we were given the modulus of A is 2, so we can start to put in the values, the B, the values over here, and the modulus of A, modulus of B over here, and the cosine of 60 can be evaluated. Alright, so from there we can get the OM modulus squared is equals to this, and therefore we can get the magnitude of OM itself. Right, now in the last part of the question, the objective of the last part of the question is to find the shortest distance in this form, K times the modulus of A cross B, where K is to be determined and it must be an exact value. Alright, so now looking at the diagram, we have the point A, then we have the point M over here. So the shortest distance of A to the line OM is actually this distance, and we can always use the cross product formula. So we're going to take the vector OA, we're going to cross with the unit vector parallel to OM. The unit vector parallel to M is actually OM divided by the magnitude itself. Alright, so since we know what is OM already, and the magnitude of OM we also know, we could actually take out all those numbers and put it here. So now we will do the cross product term by term. Alright, so we have A cross with 3/5 A, so you will have A cross A cross with 2/5 B, so you will have 2/5 A cross B. Now A cross A is actually the 0 vector. Alright, we've seen this before, so we will be left with the 0 vector plus this vector. So in the end we can take out the 2/5 out to combine with whatever numbers that we had previously, and whatever that we have now left in this modulus is just A cross B. So now we have already achieved our objective. The shortest distance is written in the form K times the modulus of A cross B, and in this case the K has this value. Alright, so that is the end of the lecture for vectors 1. Alright, so coming soon in term 3 we will be looking at vectors 2 and vectors 3. Alright, vectors 2 we will delve into lines, equations of lines, and then in vectors 3 we're going to extend lines to equation of planes.